Hello ladies and gentlemen, and welcome to Earth Science, looking at the prologue, and today we'll be discussing graphing and looking at the relationships of two different variables. It's definitely important when we go to do labs this year that this will be coming into play. How does one variable compare to another? We're going to be looking at a little bit in graphs in general. So graphs, much like we have here, okay, have two different axes. We have our x-axis, changes, there we go, right along here, our x-axis going outwards, and then we have our y-axis going up. These can be our two different variables. It could be something like we normally see in earth science, time versus maybe temperature. Okay, and we can look at the relationship between those. Remember, the x is the horizontal, y is going to be our vertical axis. Okay. Our first relationship that we commonly see is a direct relationship. In this, both variables are going to increase. Okay. So our independent variable, which is along our x-axis, is going to increase as we move out this way. And our dependent variable along our y-axis right here, there we go, okay, increasing that way. And what we get is this slant upwards, just like this. This is our direct relationship. Okay, moving upwards like that. As our independent variable increases, so does our dependent variable. Okay, so an example would be if the population of an area increases, what happens to the pollution in that same area? Well, as the number, remember, population basically means people. Okay, a little shorthand for that. So as the number of people in an area increases, usually our amount of pollution increases. People produce wastes. That waste is pollution. Another one, as the amount of carbon dioxide in the atmosphere increases, the global temperature also increases. Well, CO2 is also another name for carbon dioxide. Okay, so as the amount of carbon dioxide in the atmosphere increases, what happens to our temperatures? Well, this is called the greenhouse effect. Greenhouse effect, also known as GHG. So as the CO2 goes up from the production through cars or burning of fossil fuels, our temperature also increases. Remember, these are just examples of direct relationships, but you can just see here that constant slope going upwards. Moving on, we also have indirect relationships. In this scenario, we have one variable increases and the other one is going to decrease. And what we end up getting is a straight line that slants downwards like this. So on the bottom here, maybe time increases as we go across this way, but our dependent variable, maybe temperature, will decrease as we go down. That's it. It's another indirect relationship. Example of one is as the amount of evaporation in a lake increases. What happens to the overall depth? Well, remember, evaporation is the loss of water from a surface. So if we're losing water from the surface, most likely the depth of the lake is going to decrease or go downwards. Another indirect relationship. Another common type of relationship that we see are cyclic events or cyclic graphs. These are just a series of events that repeat themselves at regular intervals over time. Some common things are like tides. We go from high tide to low tide, back to high tide. Or moon phases. Moon phases. Okay? Full to new, back to full, with some other, of course, parts of the phases there. So a graph like that, we have so for tides, we could do time. And then along the y-axis, we could do sea level height. Okay, and we could start off with a high tide, go to low, and then high tide, going back up, low, high tide, low. And notice that we have this cyclic or this repeating high high, and high tide over time, or our case, our low tides down over here. Just another example of a cyclic graph. Okay, here's these are moon phases once again. So we can see going all the way around to over here. We're looking at our new moon in this section, and we go through seeing more and more and more, or waxing, waxing, waxing. Finally getting to our full moon somewhere in this section in here. And then as we go down, we can see the illuminated portion of the moon is just decreasing. And eventually you would end up with a new moon down here next month and a full moon. So that's another cyclic or repeating event, moving just like this. Okay, season cycles, same thing. What we have is we have time, seasons on our y-axis, and we'll go from one season to the next, one season to the next. We can look at a time versus, or another maybe date. Anything like that would also be another cyclic event. Okay. Something that we commonly use with any relationship, whether it's going to be indirect, direct, cyclic, is something known as rate of change. The rate of change is an equation that measures how fast something is happening. The formula is in the reference table on page 1. Okay, so we can go to our reference table on page 1, which is the cover. Maybe see this in your reference table for physical setting or science. One of the few times you'll be looking at this pretty much every single day. 2011 edition gives you a ton of information. But if we look up over in the equation section, and what we're going to see is a few formulas. So we go into the equation section right here, and if we look, we see rate of change. Right there, very important section, and it's our change in value over time. So going back, okay, so coming back from the reference table, we can see that our rate of change equals change in field value over time. Sometimes you'll also see me write it like this. Same thing, rate of change equals change in field value over time. This little triangle right here, triangle is delta, Greek, part of the Greek alphabet, and that means change. Just an easier way of writing it. So wherever the case may be, rate of change is our change in field value over time. Our field value is going to be a variable such as temperature, distance, okay, anything like that. And then of course time could be measured in minutes, seconds, hours, days, years, anything like that. Doesn't really matter. But that is, so we're going to be looking at some variable over time. Okay, finding rate of change, pretty easy to do. First thing we're going to do is usually write our formula. So we're going to do rate of change equals change in field value over time. Then we're going to substitute in our numbers from the word problem. We'll just use an example. Maybe it's 3 degrees Fahrenheit. Notice we always have our units over, let's do 3 hours. And that, then we solve using a calculator. 1 degree Fahrenheit over 1 hour. Or this may look like 1 degree Fahrenheit per hour. And that's it. It's as simple as a rate of change formula gets. Okay, here's an example right here of another rate of change problem. Okay, over the course of 3 years, the San Andreas Fault in California has moved 18 centimeters. How fast is it moving? So we're going to go through the problem. We're going to look at the things we need. Well, 3 years, that is our time. Then we can keep reading and we see 18 centimeters is going to be our field value. So the first thing we do is we write our formula. Rate of change equals our change in field value over time. Substitute in. Well, we know our field value is 18 centimeters over 3 years, our time. So 18 divided by 3 is 6. 18 divided by 3 is 6. Little mistake. Centimeters per year. That's it. Doesn't get any easier than that. Okay, so like I said, that's our example. It doesn't really get any easier than that, and that's just some little basics about graphing, looking at our independent, dependent, and cyclic events, and looking at rate of change, interpreting graphs. So I hope you enjoyed it. Have a good day, and see you next time.